So today we're going to talk about critical points, and as this slide states, critical points are points on a curve where a tangent line to that curve is either vertical or horizontal. Now I've tried to show in these pictures different curves. So here's a curve of a parabola going down, and a tangent line is defined as a line that hits a graph in exactly one point. So here's a tangent line. It's a horizontal tangent line. Here's a parabola going up, tangent line hitting only one point, and it's horizontal. Here's the only debatable one that you may not understand, but it's kind of true. Tangent line, it seems to only touch in one point, yet it goes through the function. We call that a tangent line, and it's a vertical tangent line, and we call it a point of inflection. Now, all these tangent lines are critical points, and we also call them those that have maximum and minimum values. We call those extrema. So if we look at this first graph, this here is a max value. It's the highest point that that curve goes to. This point right here is a min value, all right, as it states. This is neither a max or a min. We call it the point of inflection. And all max or min values are called extreme. Now, if you want a better idea of what a critical point is and what a tangent line looks like, take a look at this little slide that I've got for you. All right, as you see on the red curve, there is a white line that is touching only in one spot as it goes through. That white line is the tangent line at any given point on the graph. And anytime you see it go horizontal or dead vertical, we call that a critical point. All right? Let's kind of move on. So, in looking at these curves, we say that we have maximum and minimum values. Well, this point right here, if I were to draw a tangent line through it, or a horizontal that is tangent to the curve in this case, all right, we say this is a relative maximum. It's not the highest point of the graph, because the highest point of the graph is over here to the right. We say it does peak out at this point, and we say it's a relative max. Our lowest value of the graph is way down here somewhere, but this term right here does bottom out, and so we call that a relative min. Now, if you look at the graph over to the right, again, here's a relative max, because at that horizontal tangent line point, or at that critical point, we get a relative high point. Here's a relative min, because again, at that horizontal tangent to the curve, we get a low value. Our lowest value is somewhere way down to the left or somewhere way down to the right. But you'll notice this graph has a highest point of all, because it doesn't go up forever like the graph on the left. This is the highest point on the graph, and we call that an absolute max. And that will also have a horizontal tangent line. Okay? There are tangent lines virtually everywhere on the curve, as we saw in our example with the red curve here and the white tangent line going at any given time to the graph. But there are only special points where that tangent to the curve is horizontal or vertical. There are no vertical tangent lines in these pictures I've represented here. Let's keep moving. Now we're going to use the calculator to find extrema. And when I talk about extrema, I'm talking about max or min values. So let's grab our calculator. So the first thing we're going to do is we're going to hit the y equals button and type in our function. So y to the fourth plus 3x squared minus 5. Then we want to take and graph this. And what I'm going to choose to do is just see what shows up in our standard window. So I'm going to hit the zoom button on our calculator. And if you see number 6, it says zoom standard, which is going to graph from -10 to 10, both on the x and the y axis. So I hit number 6. and I look at the graph represented. Now, it appears that this looks parabolic in shape, or goes to the left forever, to the right forever. And if you think about the end behavior, which is something we talked about a couple of days ago, we know this is probably true, because since x to the fourth is the only thing that matters as I go to positive infinity, the y value goes to positive infinity. As I go to negative infinity, the y value goes to positive infinity. And this appears to be right. So what I need to do then is I need to find where the low point of this graph is. To do that, we're going to look for the minimum value. I will hit second and the trace button, which has calculate above it, and it says find my minimum value, 3. It's going to ask me to go to the left of my lowest point, so I'm going to move a little to the left. I'm going to hit enter. Then I'm going to go to the right of that lowest point. I'm going to hit enter again. Again, that calculator does the dumb guess thing. And notice what I have is I have this value here of negative 1.15 e to the negative 6. That's scientific notation, which means it's pretty much 0. All right. So if I look at this graph, I know that that low point is roughly at 0, and then the y value of that is going to be roughly at negative 5. So, given that, I say my critical point is at 0, negative 5. And I have a minimum, because it is the lowest point, of negative 5 at 0. That negative 5 value represents a y. Where it happens is the x value. Our next example, we're going to use the calculator to find the extrema here. So I go to y equals again, and I plug in the new function, x to the fourth minus 4x cubed. What the heck, let's take and graph that in the standard window. And we notice, well, this one does something a little bit different, and I'm not seeing the entire graph. Again, it fits my end behavior. As I go to positive infinity, it appears y goes to positive infinity. As I go to negative infinity, it appears y goes to positive infinity. But something's going on down here, okay? It appears this thing's flattening out there, and it appears something's going on way the heck down here. All right, so what I'm going to do is I want to look down there and see what is actually there. So I'm going to take my window, and rather than go down to negative 10, I'm going to move down, let's go to negative 30. And hopefully I'll see what's going on down there. I'm going to graph it again. And here's my graph. And what do you know? All right, it appears that this is reaching a relative, or actually it's an absolute minimum at this point, but I have to find out what that is. So I'm going to calculate the minimum again. Second, calc, minimum, which is 3. Go to the left of that point, which it appears is here. And to the right of that point, get that blinky guy somewhere up here. Hit enter, and a third time after the guess. And so I'm at roughly 2 and negative 27. So my extrema, or my critical point, was, I believe, once again at 3 and negative 27. So I have a absolute min of, and I'm using the y value here, negative 27 at 3. Let's go to the next example. We're going to use the calculator to find the extrema of this function. Once again, I've gone to my y equals. I've plugged in the function. I'm going to look in my standard window once again. So that's zoom 6. And here it starts graphing. Now it appears here I have a horizontal tangent line at this point here and at this point here. So what I'm going to do is I want to see these a little bit better. I'm going to blow this up, and I'm going to do it a little bit differently. I'm going to do it in a box zoom. So I'm going to go zoom, box, which is number 1. I believe we've done this before. And I'm going to take my blinky guy, and I want to blow up this whole area here. So I'm going to start my box somewhere up here, hit enter, drag my box over, and down. A little too far down. All right, now if I hit enter, I'm going to blow up that area in this box. And there we go. And it should be pretty easy to calculate. These are both relative maximums and relative minimums because the graph continues to rise and continues to fall. So let's find this first. We're going to find the relative maximum. We're going to calculate, once again, the maximum this time, which is 4. It's going to ask me for a left bound, so I need to go to the left of that high point. It's going to be somewhere over here. I'm going to hit enter. And it asks me to go to the right of that point. And I have, again, this looks like 0 because it's 1.5 times 10 to the negative 6. And again, that's negative 4.8 times 10 to the negative 12. That's 0 again. So what I have in this graph is this point right here is at 0, 0. Should probably switch colors because it's kind of hard to see. And now let's go back to our graph and find the other point. We're going to find this point down here. And we're going to calculate. This time we're going to calculate a minimum. So I hit 3. And it says go to the left of that minimum point. That's left enough. I hit enter. And it says go right of that point. So here I go. To the right of that point. And I'm going to hit enter. And guess enter the third time. And it's going to calculate that value to be about 1.3 and a negative 4.08. So this is roughly 1.3 and negative 4.08. So here's what we say. We say we have a relative min of, and I need the y value once again, negative 4.08 at, and I want the x value here, 1.3. I have a relative max of, I need the y value, 0, at the x value, 0. Done. Moving on to the next example. This one's a little uglier, so let's go ahead and plug that into the calculator. All right, so here's how I chose to plug this into the calculator. I put the first term, x to the 2/3, in a parentheses by itself. Notice the 2/3 exponent is in a parentheses. Then I multiplied by, and I put the entire next term, 6 minus x to the 1/3, in parentheses. And notice once again, the 6 minus x quantity is in its own set of parentheses, and the 1/3 is in its own set of parentheses. I'm going to try to graph that guy in the standard window, see what I get. And so this guy goes down, and it appears that it's going to jump up and go down again. All right. Now, very difficult to find critical points that are at certain instances where it comes to a point. Let me show you what I'm talking about. It didn't make a whole lot of sense. If I box zoom this, and I want to look at just this little piece here, and I take and blow that up, I see my graph comes down. It actually goes to a point. Okay, and the definition of tangent lines at a sharp point like that is that there won't be a tangent line. Just something you got to know. So if you see a graph coming to a point like an absolute value, in theory, there is not going to be a tangent line at that point. The only tangent lines that are going to exist are on rounded mounds, if you will. All right. So once again, I'm going to go to zoom. Zoom, let's try it again. 6. And the only rounded portion of this graph is the portion we saw over here. So I'm going to use the calculator to find this rounded portion over here. I'll go second, calc. I'm going to find a relative max. I'm going to go to the left of that, hit enter. To the right of that, and my calculator just went away. Wonderful. I should probably reload this. Sorry. So we'll do that. All right, so the calculator is back. I hit enter once again, and it calculates that point to be about 4 and 3.17. So if we had a graph that looked like this point right here that had the horizontal tangent was 4 and 3.17. This is a relative max of the y value, which is 3.17 at 4. Keep on moving. All right, now, it says in the graph of x to the 4th minus 4x cubed, x equals 0 is a critical point. We want to know what type of critical point is it, a max, a min, or a point of inflection. Now, it's going to be easier to tell what a point of inflection is if the graph is already there and I'm telling you that the point at x equals 0 is a critical point. So let's go ahead and graph that. So I've plugged it into my calculator. I'm going to zoom standard it. Here's my graph. And it looks like x equals 0 is a critical point. Let's zoom in on that and see what we think we've got. So we're going to zoom, and I'm going to box that once again. Make it a really small box and really zoom in on that point. So I'm going to hit enter. Drag that box over. Go down. And now I'm going to zoom in on the point 0 and see what I've got. So if I look at this graph, and I'll redraw it over to the left here, my graph looks something like this. So if I want to draw a set of tangent lines, at this point my tangent line looks something like this. At this point my tangent line looks something like this. At this point, which is the point x equals 0, my tangent to that curve is dead horizontal. Now, if my tangent to the curve is dead horizontal, and this is neither a high point, which it's not, nor a low point, it doesn't appear on the top of a hill or the valley of a ditch, if you will. If it's not a max or a min, then it's got to be a point of inflection. All right. I realize that in our first slide we showed the point of inflection had a vertical tangent line to it, but really all that it's showing is my tangent line moving from negative to negative and going to 0 at some point. So if it's not a max, it's not a min, then it's a point of inflection by just subtraction, if you will, or deduction. All right. Last. Okay, so here's a word problem. And this one's a little difficult. You can read it. Now, what we need to do is we need to draw a picture of this. So we have a box. It's open. And it's got a square base. So the base is x by x. The height, I don't know. I'm going to call that y. And we want to know what is going to be the dimensions of the box in order for it to have a maximum volume. The trick is I've got to make it from 48 square feet of material. Well, square feet, we're talking surface area. And surface area talks about, well, if I were to cover this in wrapping paper, how much paper would I use? Well, you can see that since the bottom is a square, I'm using x squared amount of material for that. Now the sides are all the same because the base is square. The sides are all x by y. And there's how many sides to a box? 4. So my surface area equation is x squared plus 4xy. The volume of the box is what we're trying to maximize because we're looking for the largest possible volume. Volume of this figure is length times width times height. And in this case, I'm going to call my length and width my base, x by my height, y. All right. Now the problem is, if I want to maximize this, I need to have it in one variable and then be able to graph it. So in order to do that, I have to take and write an equation only in terms of x. Luckily, I have another equation up here, and we've been studying two variable systems lately. So what I'm going to do is, instead of calling this just the surface area, I'm going to set it equal to 48 because that is the surface area of the box. I'm now going to get y by itself and make a substitution. So what I have is I have 4xy equals 48 minus x squared. Getting y by itself, I have y equals 48 minus x squared all over 4x. And since that equals y, I'm going to substitute into this y here, leaving me an equation with only one variable for volume. All right? Volume then will equal x squared times the quantity 48 minus x squared over 4x. I can clean this up just a little bit and call this x times 48 minus x squared all over 4 because those x's reduce. What I'm now going to do is I'm now going to rewrite this just one more time and say that's the same as 1/4 x times 48 minus x squared. And this is describing my volume. I want to maximize it. So I'm going to plug this into the calculator and look for its maximum. So I've got it in my calculator. I'm going to graph it in that standard window once again. So zoom 6. And here's my graph. And I notice I'm looking for the highest point, which appears I mean, it's going to go up here forever, but it appears to be way up here. I'm going to have to find that point. So I want to look way up. I'm going to adjust my Y scale so that instead of going to 10, let's just go to 100 for kicks. And then I'm going to graph that again. So there's the down, there's the up, and hey, it maxed out right here. Now remember, my Y values are talking about volume. So I'll get my maximum volume at this point for the X value. I'm going to calculate the maximum. Going to go to the left of that high point, hit enter, go to the right of that high point, hit enter again, and get rid of the guess. So this says I have a max of 32 at roughly 4. So max 32, that's my Y value, which is actually the volume. And at 4, which is my X value. Now if we go back to the original, it said, what are the dimensions of the box? Well, what I've got is I've got my X dimension. So my X value is 4. I've got to find my Y value. To find the Y value, simply plug back up to here. I have 48 minus 4 squared, which is 16, all over 4 times 4. So 48 minus 16 is 32 over 16, which equals 2, and that's my Y value. So my dimensions of maximum value are at an X value of 4 and a Y value of 2. Again, another long one today. Here's the questions for you to answer. Find the extrema of this function, and then do your best to try and solve this max-min word problem. We'll see you tomorrow.